Bismillahirrahmanirrahim. Assalamu alaikum students. Welcome to our 16th lecture of MTH108 Business Math 1. Today we will start our chapter 7, which is about exponential and logarithmic functions. What are the main topics of this chapter? The characteristics of exponential functions, to know the applications of exponential functions, and to know the logarithms and logarithmic functions. So these are the main topics which we will deal in this chapter. And what are the objectives of this chapter? To discuss the nature of exponential functions, their structural characteristics and graphical behavior. To present a variety of applications of exponential functions. To discuss the nature of logarithms and equivalence between exponential and logarithmic forms. That what is the relation between logarithm and exponential function. Again, to discuss the characteristics of logarithmic functions and to present a variety of applications of logarithmic functions there. That is where we can use our exponential functions in daily life and what are the applications of logarithmic functions in daily life. Before defining the exponential function, first we recall some basic algebraic facts which we have studied in our algebra in school. First we will see some properties of exponents and radicals. Now all of us have studied these properties of exponents and radicals, but for the sake of review, let us quickly have a look at them. If a and b are positive numbers and m and n are real valued numbers, then our property 1 says that b to the power m into b to the power n is nothing but adding the powers. That is, whenever b is the base and m and n are the exponents, that is, whenever the base is same, the powers will be added up. We have the same base b and the powers are different, so we can write them as with the same base b and adding the powers as m plus n. For example, we have, let's say, 2 square into 2 cube. Here the base b is equals to 2. For the sake of understanding, we write b is equals to 2. M is 2 and n is equals to 3. So we have the same base with different powers. What we will do, we will write the single base with the powers added. That is 2 plus 3, which is 2 to the power 5, which is nothing but 32. Okay. For example, we have a variable with the power 6 multiplied with the same variable with the power minus 3. Then here the base is x. b is equals to x. We will write it in the form of a single base just by adding the powers, that is 6 minus 3, and we obtain x cube. One more example, if we have y square into y to the power 8, again we have the same base y. We will write it in the form of a single base y with the powers added, that is 2 plus 8, which is equals to y to the power 10. Or if we have a base y square into y to the power 1.8, what we will do, we will simply write it in the same base with the powers added, that is 2 plus 1.8, which is y to the power 3.8. If we look at the conditions that a and b, in this property we have only used b, they are positive numbers, and m and n are real valued numbers, which means that in our last example, y square into y to the power 1.8 is allowed. That is, the value of m and n can take any real value and not only positive integers or negative integers. So from this property, maybe you have recalled the other properties of exponents and radicals as well. Our second property is that when we take the ratio, that is b to the power m divided by b to the power n, with the condition that b should be different from 0. First we simplify it. This is nothing but b to the power m. Again, what we want to do, we have the same base with different powers, and now in the ratio form. The first property was with the same base with different powers in a product form. Now the aim is the same, that is, we want to write this ratio in a single base with the powers added or multiplied or subtracted. This we have to see. B to the power m as it is. This is nothing but b to the power m into b to the power minus n. That is, whatever the quotient, whatever the power of the quotient is, we can write it simply the product of the numerator into the denominator with the negative power. So now we are reduced to our property 1, which says that we have same base but different powers. So we will add the powers and we obtain b to the power m minus n, and definitely with the condition that b should be different from 0, or in particular the denominator should be different from 0. For example, we have x to the power 6 divided by x cube. This is nothing but writing as x to the power 6 into x to the power minus 3. The ratio or the denominator will come as a product with the negative power, and now we can write it in the form of a single base with powers added, that is 6 minus 3, which is equals to x cube. Let's take one more example. 3 to the power 5 divided by 3 square. Now to calculate the 3 to the power 5 is somewhat lengthy. We will simplify it first by writing as 3 to the power 5 into the denominator will come as a product with the negative power, so it will be 3 to the power minus 2. Now we have the same base, so we will write it in the form of single base with powers added, and we obtain 3 cube, which is nothing but 27. So the ratio 3 to the power 5 divided by 3 square looks a bit lengthy or difficult to solve, but when we use the property of exponents, we simplify it and we are left with 3 cube, and it is easy to solve. That 3 cube is 27. Okay, now we come to our third property, which says that b to the power m whole power n is nothing but the product of both the powers, that is m into n. Or we can also write it as, since it is the product of both the powers, we can also write it as n first and whole to the power m. So the power of power is nothing but the product of powers. For example, we have our 10 cube whole square. Okay, this is nothing but 10 cube into 2, and simplifying the powers or taking the product, we obtain 10 to the power 6, and now we can easily simplify it by writing as 1 with 6 zeros. Okay, one more example in terms of the variables. We have x to the power minus 2 whole to the power 5. This we can write as x to the power minus 2 into 5, that is multiplying both the powers, and we obtain x to the power minus 10. So this property tells us that if we have a power of power, then on the same base, then it is nothing but the product of both the powers. Okay, our fourth property says that we have two positive numbers a and b, both with the same power. Then we can easily split the power by taking the power on a and on b separately. For example, if we have two unknowns x and y whole square, then we can simply split the power on each term of the product. That is, splitting the power on square and on y, splitting the power on x, and on y we obtain x square y square. This property basically tells us that the power of the product AB is same as product of the powers. That is, either you take the product and then the power, or either you take the power and then the product, you obtain the same result. That is, the power of the product is same as product of the powers. For example, we have 3 into 2 whole cube. Okay, what we will do, we will simply split the powers. We will take the powers first and then the product, that is 3 cube into 2 cube, and we obtain 27 into 8, which is 216. Also, if we simplify it, we obtain 6 cube, and 6 cube is 6 into 6 into 6, that is 36 into 6, which is 216. Or this property also tells us that we can also change the order, which means that either we take the power on the second one first and then on the first one. It's the same because it is the product, and we obtain the same answer. Okay, now we come to our fifth property, which is about the radicals. We have also seen this property in our algebra classes in our school. Okay, what does this property say? Let's revise it. If we have a base b with a power in a ratio form, that is m over n, then this is nothing but taking the power m whole to the power 1 over n, because m into 1 over n is m over n, and by property 3 we are basically taking the power m and then the whole power 1 over n. Okay, how we write is b to the power m and nth root. Similarly, we can take the power 1 over n first and whole to the power m, which is same as writing the nth root of b whole to the power m. So if the power occurs in the form of ratio, we can split the power in the form of product as m into 1 over n, and we can use the rules of radical, that 1 over n will be the nth root of b to the power m, or we can take the nth root first and then the power m. Okay, now some easy examples. If we have 8 to the power 2 by 3, then 8 to the power m will be 2 whole to the power 1 by 3. 8 square is now 64, and 1 by 3 is the cube root. We know that 4 cube is 64, and taking the cube root we obtain 4. Now what do? We take the 1 over nth power first, that is 8 to the power 1 by 3 whole square. We know that 2 cube is 8 basically, into 1 by 3 whole square. The inside power cancels out and we are left with 2 square, which is 4. So we obtain the same answer. Either we take the root first and then the power, or the power first and then the root. In terms of the variables, if x has a power 3 by 4, then this is nothing but x cube with the 4th root, or this is nothing but the 4th root whole cube. That is, either we take the root, radical sign and then the power, or first the power then the radical sign, it's the same. Now sixth property, which we use very often, is if a positive number has a power, has the exponent 0, then this is nothing but equals to 1, with the condition that b is different from 0. For example, if we have 100 to the power 0, then this is equals to 1. No matter how big the number is, negative values are not allowed, because in the beginning we have said that let a and b be positive numbers. So no matter how big the number is, any positive number to the power 0 is always equals to 1. Similarly, the variable x to the power 0 will be equals to 1, and this variable x to the power 0 is nothing but a constant. If we recall our previous lecture, where we have seen that a constant is a polynomial of degree 0. Seventh property, which we have already used and we know it by heart, that any positive number to the exponent 1 is the same positive number. That is, b to the power 1 is nothing but b. For example, x can be written as x to the power 1. Since x to the power 1 is so obvious, we never write it x to the power 1. Particularly when we write our polynomials, for example a linear function, we never write the general form of our linear function a into x to the power 1 plus b into x to the power 0. We never write it. We know it by heart that any variable, any positive number to the power 0 is always 1. Any positive number to the power 1 is the same number. Or for example, if we have a product xy, then this basically means that the product has power 1. And now by using our property, we can split the power. This is nothing but x to the power 1 into the y to the power 1. Now we see some more properties of exponents. Eighth property, we have already used it, that any positive number to the negative power is nothing but 1 over the number to that power. We have already used it in our first property. If we go back, in our second property, that b to the power m over b to the power n is nothing but b to the power n numerator as it is, and 1 over b to the power n is b to the power minus n. So any number, positive number with a negative power, is nothing but 1 over the number with the positive power. So if we have a number with a negative power, we can simply write it as 1 over and the power becomes positive. Okay, with some condition that the number should be different from 0, because if b will be equals to 0, then division by 0 is not allowed. And now some examples. Example says that if we have 2 to the power minus 3, so this is nothing but 1 over 2 with the positive power 2 cube. 2 cube is 8, so this is 1 over 8. Okay, if we have in terms of variable 1 over x to the power minus 2, so whenever we have the number with a negative power, we simply take the reciprocal of it to reduce the negative power, and we obtain the positive power. So how we will obtain the positive power in this case? This is equals to 1 over x to the power minus 2. Okay, this is nothing but 1 over x square, and simplifying we obtain x square. So x square can be written as 1 over x to the power minus 2, which this property says that the negative power can be replaced by a positive power by simply taking the reciprocal. In our second example of the case of variable 1 over x to the power minus 2, we have replaced the minus power by a positive one by simply taking the reciprocal in the denominator only, where the negative power occurs. We have taken the reciprocal in the denominator, and we have got the answer x square with the positive power. Okay, now our last property. Last property says that if we have two positive numbers a and b with the ratio and with the same power, then this is nothing but a to the power n over b to the power n. This property actually says that if we have two numbers in ratio with the same power, then either we take the ratio first and then the power is same as we take the powers first and then the ratio. That is, the power of ratio is same as ratio of powers, with the condition on b that b is different from 0. For example, if we have our x over y whole cube, we have the ratio and then the power. What we can do, we can take the power first, that is x cube and y cube, and then the ratio, with the condition that y is different from 0. For one more example, we have 2 over 5 whole cube. What we will do, we will split the power, or we will take the power first and then the ratio. We obtain 8 over 125. So these were the properties, just to revise how we can use our exponents and radicals very easily, and how friendly they are to use and how important they are. Their importance we will see shortly when we will define our exponential functions. Okay, up to now we have put the condition that b should be different from 0 whenever b is appearing in the denominator. But b can take any positive value. So a question arises that what happens when b is equals to 1, which means that we are reduced to 1 to the power m, where m, the values are allowed to have any value from the set of reals, where m belongs to R. Now clearly 1 to the power m is 1 again, no matter what the value of m is. So what we are doing basically, that we have a constant raised to a variable, raised to a power which is a variable. So m is our variable here. We have a constant raised to a variable power. These type of functions are basically the exponential functions. So 1 to the power m is an exponential function, but it is of no interest to us. This is an exponential function, of course, because it can be written as the form of constant raised to a variable power. This is an exponential function, but this exponential function is not interesting. Okay, so keeping this question in mind, now we formally define what do we mean by exponential functions, and we will study their characteristics. Okay, now exponential and logarithmic functions have many important applications, not only in mathematics but also in business, economics and sciences. Means these functions are widely used in every real world phenomenon. So how we define our exponential functions? a function of the form f of x is equals to b to the power x, where b is a constant, a positive constant different from 1, and x is any real number, is called an exponential function to the base b. If we put the value of b is equals to 1 here, we obtain our exponential function 1 to the power x, in which we are not interested. So we have put the condition, the same condition as in the case of exponents and radicals, that b should be a positive number. So f of x is equals to p to the power x is a function with the condition that b different from 1 and positive number, with x as the variable allowed to take the values from the set of reals. In particular, we are saying that the exponential functions are those which are constant raised to a variable power. The constant should be positive, different from 1. And we call them exponential functions to that number base b. For example, if we have 3 to the power 2x, is it an exponential function or not? Yes, it is an exponential function, and we can write it in the form of b to the power x. How? By using the properties of exponents, which we have just studied. Now the power is a product of 2 and x, so we can write it as either we take the square first or then the power x, then 3 square will be 9, and we are left with 9 to the power x. So 3 to the power 2x is an exponential function which can be simplified by using the properties of exponents and written as 9 to the power x. One more example, 2 to the power minus x. Is it an exponential function or not? Clearly it is an exponential function, but to see this we have to use the property of exponents. That is, here we have a constant base 2 with a variable power x, but the power is negative. So we want to remove this negative power to the positive one. How? Just by taking the reciprocal. That is, we write it as 1 over 2 to the power x. And we can also write it as 1 to the power x over 2 to the power x, because 1 to the any variable power is same as 1. And now we will use the property of the quotients, that either we take the power first and then the ratio, or we take the ratio first and then the power. So 2 to the power minus x is an exponential function with the base 1 by 2 and power x. And definitely 1 by 2 is different from 1 and positive. So if an exponential function is not clear, then, or not written in the general form, that is b to the power x, then we can use the properties of exponents and simplify it and write it in the exponential form, that is some constant to the variable power x. The constant different from 1 and the constant is positive. Now we come to a word problem where we very often use these exponential functions. Okay, in many natural processes, the rate at which something grows or decays depend upon its current value and is exponential. For example, the manner in which the body discharges medication, or for example, the population growth. That is, the rate at which the population increases or decreases depends upon the current value, that is the total number of people present in that community at that particular time. So these type of growth or decay are exponential in manner. One example is that when the body discharges the medication. For one particular type of medication, suppose that half of the medication in the body is excreted from the bloodstream by the kidneys every 3 hours. Suppose a body is given a medication, and after 3 hours the body discharges the medication with the rate of the current value. That is, after 3 hours the body discharges half of the amount of the current value. So if an initial dose is of 100 milligram, then the content in the body after 3 hours would be half, because the body is discharging the medicine half in the quantity after every 3 hours. So the quantity in the body after 3 hours would be the half of the current value. That is, the current amount is 100 mg and half of it, which is 50 mg. So after 3 hours the amount of medicine in the body will be half of the current value. Half of the current value, which is 100. So after 3 hours the medicine in the body will be 50 mg. After 6 hours the amount left in the body will be half of the current value, which is 50 now. So half of the current value, which is 25. That is, after 6 hours the amount of the medicine left in the body is only 25 mg. If we say that time t is equals to 0, the amount is 100 mg. Okay. After 3 hours, if we say t is equals to 1, basically implies after 3 hours. Here what we are doing, basically we are rescaling our hours. That is, initially the amount was 100 mg. After 3 hours there is some decay in the amount of the medicine in the body. So we call this 3 hours as t is equals to 1. The same thing which we have done in our chapter 6, when we were given the data points and the number of years and the current and the cricket player's salary or the average player's salary. The time was given in 1985, 81 and so on. We have rescaled the time. Here we will also rescale the time in terms of, that is, after 3 hours the time is 1, t will be equals to 2 after 6 hours, and after every multiple, for every multiple of 3 we will obtain the rescaled time as 0, 1, 2 and so on. So when time t is equals to 0, the amount was 100 mg. After 3 hours, let's say t is equals to 1, the amount was reduced to half of the current value, that is half of current value 100, which is 50. Okay, after 6 hours means t is equals to 2, the amount is further reduced to half of the current one is now 50, and the amount is reduced to half of it, which is nothing but 25. Now what is 50 here? Basically 50 is 100 into 1 by 2. If we want to use the value of 50 from our first equation, that is after 3 hours, we obtain 100 into 1 by 2. So by putting the value of 50 in our equation, we obtain 100 into 1 by 2 into 1 by 2 is equals to 25. That is it is the value when t is equals to 2. Or we can simply write it as 1 by 2, 100 into 1 by 2 whole square is equals to 25. Now what will be the value when t is equals to 3? That is after 9 hours we have half of the current value. Okay, half of the current value is 25 into 1 by 2, which is equals to 12.5, and By putting the value of 25 from previous equation, we obtain 100 into 1 by 2 square into 1 by 2 is equals to 12.5, and simplifying, this is 100 into 1 by 2 whole cube is equals to 12.5. So continuing in this way, we have observed that there is a particular pattern which is repeating after every 3 hours. So after n 3 hour of period, the general form will be, or the amount left will be equals to 100 1 by 2 to the power n, which we call as A. So this is our time on the x-axis with 3, 6 and 9, or on the y-axis we have amount. Okay, since we have rescaled our time, so this will be equals to 1, 2 and 3. Let's say if this is equals to 100, this is equals to amount 50, this is 25 and so on. So at time t is equals to 0, the amount was 100 mg. At time t is equals to 1, that is after 3 hours, the amount was 50. After 6 hours, the amount was reduced to half, which was 25 mg. And after 9 hours, the amount was further reduced to the half of the current value, which is 12.5. Now joining all the points, this is the graph of our amount left in terms of the time, which is 100 into 1 over 2 to the power n. Now we are further asked that since we can observe that the excretion of medication from the body is happening continuously, so time n is a continuous function allowed to take non-integer values as well. That is, the graph tells us that the excretion of medication is a continuous function of time. So if we are further asked to find the amount A after time t is equals to 10.5 hours, first we have to rescale our time. T is equals to 10.5 hours, t is equals to 1, 2, 3 and 4, so on. We know that 10.5 is same as 9 plus 1.5, and we have seen that after 9 hours the value of t was equals to 3, and 1.5 will be added as half. So after 10.5 hours we have rescaled our time as 3.5, and we are interested in finding the value of the amount left after 3.5. That is, A is equals to 100 into 1 by 2 to the power n, which is now 3.5. Okay, which means that this is nothing but writing 100 1 by 2 whole cube into 1 by 2 to the power 0.5 by using the properties of exponents. Now 100 1 by 2 whole cube is same as 1 over 2 cube, and we obtain as 1 by 8, and here we obtain 0.5 under root, which is 100 by 8 into 0.707 approximately, and by simplifying all this we obtain 25 by 2.818, which is nothing but 8.8375 milligrams of the medicine left in the body after 10.5 hours or rescaling n equals to 3.5. Now we are also interested in finding the amount when time is 15 hours. Again we have to rescale our time from 15 hours, which is nothing but writing as 3 into 5. So we obtain that t will be equals to 5, or n is equals to actually 5. Yes, so the amount will be, the function of n will be 100 into 1 by 2. Now n is 5 here. We obtain 100 into 1 by 2 to the power 5, which is 100 into 1 over 32. And what do we get? 100 by 32, which is 3.125 mg. So we have seen that our real world problem was nothing but an exponential function, and how we can formulate the exponential function. We have slowly started with t is equals to 0 by rescaling our n, that is for initially t is 0, after 3 hours t is 1, and so on, and we obtain the general formula for the amount left after any time. Since the function of excretion of medicine from the body is continuous, what we can see that our amount function is continuous, and we can find the amount at any particular value. Now we come to some special classes of exponential functions. There are different classes of exponential functions, and one important class is that having the form y is equals to f of x is equals to ab to the power mx, where a, b and m are real valued constants and x is a real valued variable. With the condition on b, that provided that b is positive and b is different from 1. Now this is a class of exponential function, but for the sake of understanding, we consider that a is equals to m is equals to 1. Then our exponential function is reduced to b to the power x. Y is equals to b to the power x with b positive and different from 1. Okay. So we have defined an important class of exponential functions and simplified it just to understand that when a and m are 1, our exponential function is y is equals to b to the power x for positive b values of b different from 1. Okay, and now we are interested in the graph of these type of functions. Okay, if we consider the function f of x is equals to 2 to the power x, then how we can plot the graph of this exponential function? Clearly it is an exponential function with base b is equals to 2 and real valued variable x. In order to see the graph of this function, we have to take some values of x and the corresponding values of y. Okay, now these are x and this is 2 to the power x. So since x is a real valued, so we also have to consider some negative values as well, which means that if x is 0, 2 to the power 0 is 1 by the property of exponents. Whenever x is 1, we obtain 2. Whenever x is 2, 2 square is 4. In the case of 3, 2 cube is 8. And now some negative powers. Whenever x is minus 1, we obtain basically 2 to the power minus 1, which is 1 over 2. Since we can remove the negative power, replace the negative power by a positive one, and this is 0.5. Okay, we take some more values. When x is minus 2, 2 to the power x will be equals to 2 to the power minus 2, which is nothing but 1 over 2 square, which is 1 over 4, which is 0.25. When x is minus 3, we obtain 2 to the power minus 3, which is 1 over 2 cube, which is 1 over 8, and after simplifying we obtain 0.125. And when x is 0, this is 1. In the case of 1, when x is 1, this is 2, that is this point. When x is 2, this is 4, and so on, continuing in this way. 1, 2, 3. And now the negative powers. When x is minus 1, this is 0.5. In the case of minus 1, this is this point. Continuing in the case of minus 2, we obtain 0.25, and so on. And now joining all these points, we obtain some graph like this, which is a graph of exponential function 2 to the power x. Now, what we have observed from this graph, that for all values of x, no matter whatever the value of x we are taking, positive or negative, for all values of x, the output f of x is positive. That is, the graph strictly lies above the x-axis on the positive side, and our output f of x is an increasing function. That is, with the higher the values of x, the higher the output f of x. Or if x1 is less than x2, for example 2 is less than 3, the image f of x1 is less than f of x2. That is, when x is equals to 2, we obtain 4. When x is equals to 3, we obtain 8, and so on with the negative values as well. So we have plotted the graph of our exponential function 2 to the power x, and now we will plot the graph of 3 exponential functions. When first function is the same one, 2 to the power x, our second function, let's say 3 to the power x, and our third function, h of x, say 5 to the power x, where b is clearly greater than 1. Okay, and now why we are considering 3 exponential functions? Because we want to see the behavior of exponential functions, how they basically behave. Again, we have to take the values of x and the particular values of the output. For the case of 2 to the power x, we have already solved. Okay, when x is 0, all of them are 1. When x is 1, we have 1 power. When x is 2, we have 4, 9, 25, and now the negative values. When x is minus 1, we have 0.5, 1 over 3 is 0.33, 1 over 5 is 0.2. When x is minus 2, we have 1 over 4 is 0.25, 1 over 9 is 0.11, and 1 over 25 is 0. Okay. First we plot the graph of 2 to the power x. This was like this, and then going this way. Okay, now we plot the graph of 3 to the power x. It also passes through 1, 0. Okay, this is somewhat like this and a bit more steeper than 2 to the power x. And now the graph of 5 to the power x, which also passes through 0, 1 and continues in this way. So what we have observed from these three graphs, basically they are in the same manner, they behave in the same manner, they all pass through 0, 1, and the higher the magnitude, that is if the magnitude is 3 greater than 2, or the higher the magnitude, the graph is more closer to the positive y-axis. Now we have compared three graphs of exponential functions when b is strictly greater than 1. And keeping this picture in mind, now we will give the general characteristics of the exponential functions whenever b is greater than 1. So what are the characteristics of functions? F of x is equals to b to the power x, where b is greater than 1. Now we have seen that each function is defined for all values of x. That is, the domain is the set of all real numbers. Now the graph of f lies entirely above the x-axis, no matter whatever the magnitude is, which means that the range of the function is only the set of positive reals. That is, if we go back to our previous slide, all the graphs lie above the x-axis, which means that the range of the graphs is only the positive reals. Now the y-intercept, no matter the value of b is, whatever the value of b is, occurs at 0, 1. That is, when x is 0, every graph crosses the y-axis at 1. Whenever x is 0, the graph has a y-intercept as 0, 1. And there is no x-intercept. In the case of y is equals to 5 to the power x, it may look like that the graph crosses the x-axis, but it is not very well drawn. In fact, they keep on continuing along the negative x-axis and they do not intersect the x-axis at all. So there is no x-intercept. Fourth property is that y is always an increasing function. That is, whenever we have two values x1 and x2 with x1 less than s2, then the image will be always less than, image of x1 will be always less than the image of x2. So the output is always an increasing function. Fifth property says that the graph approaches the x-axis as x attains more negative values. So let's go back to our graphs again. The graph approaches the x-axis means that all these graphs never cross our x-axis, never intersect, but they only approach as x becomes more negative and negative. And the larger the magnitude of the base b, the greater the rate of increase in y as x increases in value. What does this mean? the larger the magnitude of the base p, that is 3 is greater than 2 and 5 is greater than 3, the greater the increase in y, the graph is more close to the positive y-axis. Now let's quickly revise or test ourselves that have we clearly understood the concept of exponential functions. For example, if we have 4 to the power t square minus 2t plus 1, then is it an exponential function with a base b is equals to 4 and some power t square minus 2t plus 1? Immediately if we look at the function, we say that no. But this function or the exponent can be simplified as t minus 1 whole square. Opening the square of a minus b, we obtain the same exponent, that is t square minus 2t plus 1. And now the exponent is t minus 1 whole square and the base is 4. So this is clearly an exponential function. One more example, t cube with 4th root. This is nothing but t cube and this is t to the power 3 by 4, and clearly yes, it is an exponential function. One more example, under root 2 into x to the power 5 and a question mark. What would be the answer? Is the given function exponential or not? If you say that the given function is exponential, then the answer is absolutely wrong, because if we look closely, it is a polynomial in fact of degree 5 and not an exponential function, because here we have variable as the base, but the exponential functions are defined as variable appearing in the exponent as the power. So this is not an exponential function. Okay, up to now we have seen the graphs of exponential functions when b is strictly greater than 1. But what happens when b lies between 0 and 1? These type of functions are also exponential functions. For example, if we consider our function f of x is equals to 1 by 2 to the power x, then here the general form of our function is f of x is equals to b to the power x, where b lies between 0 and 1, strictly between 0 and 1. For example, if b is equals to 0.5, then what will be the behavior of such kind of exponential functions? Will it be the same when b is greater than 1 or somewhat different? For this, we have to first find the graph of this function to see how much this function is similar to the case when b is greater than 1. And to find the graph, we have to take some values of x and the corresponding values of our f of x. Okay, x and f of x. When x is 0, clearly we obtain the answer 1. When x is 1, the answer is 0.5. When x is 2, the answer is 1 over 2 square with 1 by 4, which is 0.25. And now the negative values. When x is minus 1, what will happen? This is nothing but 2. And you have to use the property of exponents to see that when x is minus 1, okay, I write it here. When x is minus 1, this is nothing but 1 over 1 by 2, which is equals to 2. Okay, when x is minus 2, we obtain the value 4. And now we give the graph of this function. Okay, at x equals to 0, this is 1. At x equals to 1, this is 0.5, this point equals to 2, this is further reduced 0.25. At x equals to minus 1, this is 2, oops, this one, and at x equals to minus 2, this is 4. And now we will connect all the points starting from the left one. Not very well drawn. And so on. This way, continuing in this way, and continuing in this way. So this is the graph of 1 by 2 to the power x. Now, does it look like the graph of b to the power x when b is greater than 1? Or anything else comes in mind? Okay. First we observe this graph that for all values of x, the range, the output is only positive values. That is, for all x, f of x is positive. That is, the graph does not lie below the x-axis, lie entirely above the x-axis. And the second thing which we have observed, that the graph is a decreasing function. F is a decreasing function. So the first property is the same as with the case of b greater than 1, and the second property is totally opposite. As in the previous case, the graph was an increasing function, and now the graph is a decreasing function. Okay, now as with the case of b greater than 1, we will compare 3 graphs, that is with 3 different values of b lying between 0 and 1. The first one, we will take the one which we have already solved, that is 1 by 2. The second one, we take 0.25 to the power x, and the third one we take 0.9 to the power x. And I will not take the values of these x and y, but you have to take the values of x, let's say 0, 1, 2, and 2 negative values, minus 1 and minus 2, for each of the functions. And now if this is our 1, then first we plot the graph of 0.9. This is, we have to change our 1. This is like this. Let's say this is our 1. Graph of 0.9 to the power x. Okay, now graph of 0.5. Okay, 0.5 to the power x. Okay, and now the last one, the graph of 0.25. 0.25 to the power x. So what conclusion do we get? We have more or less the same properties as with the case of b greater than 1, and now we will see the properties and the graph to see what do we mean by the properties. Okay, so the characteristics of the functions f of x is equals to b to the power x when b is strictly lying between 0 and 1. Now each function is defined for all values of x, that is, the domain is the set of real numbers. The same property as we had when b was greater than 1. The graph of f lies entirely above the x-axis, means the range is the set of positive reals. Again the same property. The y-intercept occurs at 0, 1. Okay, let's go back at the graphs. Yes, every graph passes the y-axis at 1, and there is no x-intercept. Means that all these lines continue towards positive x-axis, but they never intersect our x-axis. Okay. Summarizing all the graphs, we define the characteristics of these exponential functions, that is the functions of the form f of x is equals to b to the power x, where b is between 0 and 1. We have seen that each function is defined for all values of x, and the domain is the set of all real numbers. The graph of f lies entirely above the x-axis, and the range is the set of all positive real numbers. The y-intercept, as with the case of b greater than 1, occurs at 0, 1, and there is no x-intercept. That is, the graph does not touch the x-intercept at all, x-axis at all. Our y is a decreasing function of x, that is, when we have two values of x1 greater than x2, then f of x1 is less than f of x2. So these four properties are similar to the case when b is greater than 1. That is, the domain is the set of all reals, the range is the set of only positive reals. We have the same y-intercept between 0 and, that is, when x is 0, y is 1. No x-intercept, except the fourth property, that in this case y is a decreasing function. The graph approaches the x-axis as x attains more positive values, and the smaller the magnitude of the base b, the greater the rate of decrease in y as x increases in value. So now we summarize our both of the graphs, that is the case when b is between 0 and 1, and the case when b is strictly greater than 1. Then in this case, this is our graph where this is the point 1, 0, 1. The graph rises, the graph is an increasing function, and the graph rises from left to right. And for the case of b between 0 and 1, this is our graph with y-intercept as 0, 1, no x-intercept. The domain is the set of all reals, and the range is the set of all positive reals. And in this case, the function y is a decreasing function, so the graph falls from left to right. So this is how we summarize the graph of exponential function when b is between 0 and 1 and when b is greater than 1. Now we define an important type of property, that is the transformation of exponential functions. For example, we are asked to find the graph of our function y is equals to 2 to the power x minus 3, and we have to use the graph of y is equals to 2 to the power x. Then this graph is obtained by shifting the graph of y is equals to 2 to the power x 3 units downward. That is, we have our function f of x, which is equals to 2 to the power x, and this is defined as f of x minus c, where c is equals to 3 now. So first we will draw the graph of our function y is equals to 2 to the power x. Since here b is equals to 2 greater than 1, so the graph will be an increasing function rising from left to right, and the graph of the function 2 to the power x minus 3 will be 3 units downward. That is, this was the y-intercept 0, 1, so minus 1 and going up to minus 2. So the graph will cross the y-axis at point minus 2. It will be again an increasing function with the different y-intercept as 0, minus 2. So this is how we obtained the graph of our function 2 to the power x minus 3 using the graph of a known function 2 to the power x. So by knowing the graph of known functions, we can transform our exponential functions and draw their graph easily. Let's look at another example. Suppose we are asked to find the graph of y is equals to 1 by 2 to the power x minus 4 by using the graph of y is equals to 1 by 2 to the power x, then how we will proceed? First we have to plot the graph of y is equals to 1 by 2 to the power x, and the graph, since b is between 0 and 1, the graph looks like this, where this value is 1, that is 0.5 to the power x. And now our function f of x has been shifted to f of x minus c, where c is equals to 4. So the graph of the function 1 by 2 to the power x minus 4 will be obtained by shifting the graph to the right 4 units. That is, if this is equals to 4, then the graph will be obtained by shifting the graph to the right 4 units, and this is the graph of 1 by 2 to the power x minus 4. So what we have done, we have shifted the graph to 4 units to the right, that is, shifted the graph of 1 by 2 to the power x to 4 units to the right. Okay. Now we come to our second class of exponential functions, that is base e exponential functions. This special class of exponential functions is of the form y is equals to f of x, which is equals to a e to the power mx, where in this case b has some particular value e. And what is e? Where e is an irrational number and it has a value as 2.718 and so on. So what happens when we replace our b by a special number e, which is an irrational number, and with the value e is equals to 2.718, then base e exponential functions are also called as natural exponential functions and are particularly appropriate in modeling continuous growth and decay process and continuous compounding of interest. So we consider two important functions, namely y is equals to e to the power x and y is equals to e to the power minus x. Okay, what does this mean? That here we have a is equals to m is equals to 1. Okay, these type of functions are mainly used in our real world problems, and we are interested to know what will be the behavior of the graph of these type of functions. So we will plot both the graphs on the same xy plane. E to the power x, okay, what is x and what is y? When x is 0, y is 1. When x is 1, we have 2.718. In the case of 2, we have 7.39. In the case of minus 1, we have 0.37. This is e to the power x. In the case of minus 2, we have 0.14 and e to the power minus x. Okay, this y. When x is 0, this is 1. When x is 1, this is 0.37. When x is 2, this is 0.14. When x is minus 1, this is 2.71. When x is minus 2, this is 7.39. And this is the graph of e to the power x and the graph of e to the power minus x. That is, if we look at both the graphs, they are basically e to the power minus x is just a reflection of e to the power x. Now the graph of e to the power x basically rises from left to right. So this is the graph of an increasing function, and the graph of e to the power minus x basically falls from left to right. From left to right, and this is the graph of a decreasing function. Now e to the power minus x is nothing but 1 over e to the power x, and we know that 0 is less than 1 over e is less than 1. Also, f of minus x is y is equals to e to the power minus x, then f of minus x is equals to e to the power minus x. That is, this graph is nothing but the reflection of y is equals to e to the power x. So both the graphs have y-intercept as 0, 1, y-intercept as 0, 1, no x-intercept, and the other properties we have already seen, that the graph of e to the power minus x is a graph of decreasing function falling from left to right, and the graph of e to the power x is a graph of an increasing function rising from left to right. And what is the domain in both the cases? The domain is the set of real numbers, and the range, if we look at the graphs, the range is the set of all positive reals. Okay. Now, if we are asked to sketch the graph of y is equals to e to the power x plus 2, that is the translated function, then what is happening? Basically, our f of x is shifting to f of x plus c, with c is equals to 2. So, first we will plot the graph of y is equals to e to the power x. Okay. And now, the graph of e to the power x plus 2 will be the graph of e to the power x shifted 2 units to the left. That is, the graph will look like this. Graph is e to the power x plus 2. That is, the graph of e to the power x plus 2 is obtained by shifting the graph of e to the power x 2 units to the left. Okay, let's take one more example of the translated function. Suppose we are defined the function y is equals to 1 minus e to the power minus mx, and let us assume that m is equals to 1. Then our function is y is equals to 1 minus e to the power minus x. Now, this is the graph of our function f of x shifted to c plus f of x where c is equals to c minus f of x where c is equals to 1. So for this, first we have to plot the graph of e to the power minus x, or what are the values of e to the power minus x? They are nothing but, and x is 0, 1 and 2. This is 1, 0.367, 0.13, and 1 minus e to the power minus x will be equals to 0, 0.632, 0.86 and so on. And we plot the graph of y is equals to 1 minus e to the power minus x. This is our domain now. Okay, so the graph will look like when x is 0, the graph is 0. The graph is starting from here now, and it will attain the maximum value approximately equals to 1, but it will never cross this line and it will be never equals to 1. So this is the graph of 1 minus e to the power minus x. So now we have seen that by knowing the graphs of the known functions, for example e to the power x, e to the power minus x, or when the base b is not equals to e, for example 1 by 2 to the power x or 2 to the power x, we can find the graphs of other functions simply by translating the graph to the left or to the right, or shifting the graph some units above or below. Now, we are interested in knowing any given function in terms of base e only. That is, we are interested in if we are given a function y is equals to f of x defined as b to the power x, we want to know that what will be how this function will be defined if we convert it to the base e. Because there are instances where base e exponential functions are preferred to those having another base. Exponential functions having a base other than e can be transformed into equivalent base e functions. And this can be done because any positive number can be expressed equivalently as some power of the base e, or we can find an exponent n such that e to the power n is equals to b, where b is positive. For example, we are given a function f of x equals 3 to the power x, and we are interested in writing this function to the base e. Here b is equals to 3. That is, we have to find n such that e to the power n is equals to b is equals to 3. Now we know that e to the power 1.1 is approximately equals to 3.004, which means that e to the power 1.1 is approximately equals to 3. This implies that n is equals to 1.1, which converts our function f of x is equals to 3 to the power x to the base e. So what will be the converted function? We had f of x equals 3 to the power x, and now 3 is equivalent to e to the power 1.1 whole to the power x using the property of exponents. This is nothing but e to the power 1.1 into x. So this is our function with base b is equals to 3 converted to the function with base e. Similarly, we can convert function of any base to the function of base e. If we want to check, then let's say at x is equals to 2, what will be f of 2 by the given function, that is 3 to the power x, which is 3 square, which is 9. And what do we obtain after converting the function in base p? It will be e to the power 1.1x, which is e to the power 1.1 into 2, which is e to the power 2.2, which is nothing but 9.025. So both the functions are approximately equal to each other, and if we are given a function in any base other than e, we can simply convert our function to the base e by finding the number n such that e to the power n is equals to b. Okay. Now we summarize what we have studied today. We have studied the properties of exponents and radicals in the beginning as a revision. Then we have studied the exponential functions, two types of exponential functions. Y is equals to b to the power x. The first case was when b was greater than 1, and the second case when b is strictly lying between 0 and 1 and b different from 1. Further, we have seen the graphs of exponential functions and the graphs of transformations. Then we have seen the exponential functions with base e called as natural exponential functions. And we have also seen the graphs of exponential functions, particularly the graph of e to the power x and e to the power minus x, and how we can convert a function of any base to a function of base e. With this, we end our today's lecture. Hope the lecture was clear to you. And in our next lecture, we will continue with our chapter 7, which is about exponential and logarithmic functions. Allah Hafiz, students.